All right. So once again, sampling variability refers to the fact that in different random samples of the same size from the same population, we're certainly going to get different values of the statistic. So the variability is going to change from one sample to the next. The sampling distribution, however, is every single possible sample that we could take from a given population. Okay? And as we looked at these graphs, we saw the different samples that came up here, and then we saw all the different samples here. Again, if we could take the mean of the sampling distribution, we would have the true value of the parameter that we're trying to estimate. Think about it. If I took every possible sample that's there and then I took the average of all those samples, it would give me the true answer. All right. How do we describe distributions? Well, we already know that we talk shape, center, spread, shape, center, spread, shape, center, spread over and over and over and over again. Okay? Now, we're going to talk about two things here called bias and variability in our estimators. So X bar is an unbiased estimator of mu. P hat is the unbiased estimator of P. Now let's take a look at our targets here. So let's imagine that we're shooting a bow and arrow. A statistic is said to be unbiased is if the mean of its sampling distribution is equal to the true value of the parameter that's being estimated. So, for example, if I take many, many samples and I average all the samples, if all those samples are equal to the true parameter, then that statistic is said to be unbiased. So, if you look at diagram A here, we've shot a bunch of arrows and they were all grouped together right here. So there was very little variability because remember, variability is describing spread. How spread out were our shots? They weren't spread out at all. So we would say that this has very low variability because they're all right in the same area. However, if I were to average all of these shots, it would not put me on target at the bullseye. Therefore, this statistic is said to have a high bias because the mean of all the samples is not equal to the true mean of the parameter, but low variability because they're all grouped together. If we look at group B, you can see they're very spread out all over the place here. High variability. But if I were to take the average of all these, if I were to average all of these dots, well, you know what? The average of all these, what's going to happen? It's going to put me right at the bullseye. So there's very low bias because the mean or the average of the sampling distributions on target. Therefore, low bias. Bias is telling us how far away are we from actually hitting the target. Variability, again, is telling us how spread out we are. So if you look at figure C, pretty spread out, large variability. Our shots were all over the place. And if I average them all out, am I going to hit the bullseye? Heck no, I'm going to be in there somewhere. So this one has high bias and high variability. What we're hoping for, or what we would like to see, would be in D. If you look at this, all of our shots were really grouped together, so low variability. And if we average them all, we hit the bullseye, low bias. So low variability, low bias. Well, what affects variability? If we take a look at these two dot plots on the right, we took samples of n equals 100 of what proportion of the population is watching the popular TV show Survivor. So the sample proportion P hat, we took a sample of 100 randomly selected people in the United States. And if you look at the sampling distribution of size n equals 100, what happened? Well, we had values all the way from about 21% all the way up to 50%. But when looking at it, it looks like the true center is somewhere around 37.5%. The true center is probably somewhere in this range here. So we would say that this sampling distribution, how do we describe it? Shape, center, spread. Well, if the true answer is 37, I would say there's low bias, because if I were to average all of these values together, it would hit the target around 37. Okay? Now, variability, well, it's pretty spread out. It went all the way from around 22% all the way up to 50%. So there was high variability, but low bias. Now, if you look at the the dot plot underneath, this, they took samples of size n equals 1,000. So the larger the sample size is, as n gets bigger and bigger, x bar, or in this case, p hat, will start to approach the population parameter p. So the larger the sample, the closer the mean of all of them will be to the true mean of the population we're trying to estimate. So in this case, look at the difference. They both hit the target. They both found a sample proportion p hat very close to the true population proportion p, around 37%. What is the difference when we jump from size n equals 100 to n equals 1,000? The variability. As n gets bigger, it's much less likely that we would choose a sample that is far away from the true population parameter that we're trying to estimate, because it makes sense. Think about our class. There's 35 students in the class. What's the true mean GPA of this class? Well, if I randomly select 2 students, I could pick the 2 lowest students, or I could pick the 2 highest students. It would be very far away from the true mean of the population of this class, mu. Those X bars could be at zero, a GPA of 0 all up to a GPA of 4.5. But if that sample gets larger and I take a sample of, say, 10 students of the 35 in this class, well, there's no way I could get a mean as low as 0 of those 10, or a mean as high as 4.5 from those 10, like I could when I only took a sample of size n equals 2. So as the sample size increases, the variability will decrease corresponding. And we'll look at the relationship between those two as we move forward. So how do I describe a distribution? For a sampling distribution, yes, for a distribution, we want to talk shape, center, spread. We have these 2 new terms, bias and variability, based off of how spread out were our values, our sample proportions, or our sample means. That's variability. And bias, if we take the mean of all the samples, do we come close to the true mean of the parameter that we're trying to estimate?